session. All right. Do you have my screen, Mrs. Atter? Salam alaikum, Mrs. Atter. Are you hearing me? Yes.
Yes, doctor. The screen is
Okay. Thank you
yes.
so much. Yes. Thank you. All right. So in this slide, I wanted to just examine the voltage profile and reliability of distributor feed at one end is playing a significant role in distribution system design. As we move farther from the feeding point, the voltage across the loads gradually decreases due to the voltage drop along the line, with the minimum voltage occurring at the farthest load point. So typically denoted as point B. So here, this is a farthest point in this single line diagram. Okay, and this voltage variation is an important consideration in system design to ensure all loads receive an acceptable voltage. Additionally, let me just add a new student. Okay. Additionally, a key disadvantage of this configuration is its low reliability. So if a fault occurs at any section of the distributor, the entire system must be disconnected from the supply to isolate the fault and repair the systems. As a result, the continuity of supply is interrupted, and it can affect all connected customers. So this is the main point. Okay, in this slide, we want to consider a practical example of a single phase AC distributor that is 300-meter long and feed from one end, labeled at point A, you can see here. And the distributor supplies two loads located at different positions along its length. And the first load is connected at point C, 200 meter from the source, drawing 100 ampere at a lagging power factor of 0.707. The second load is located at the far end, point B, 300 meters from the source, and it's consuming 200 ampere at a lagging power factor of zero point 0.8. The distributor has both resistance and reactance, which contribute to voltage drops along the line. This example is used to analyze how current distribution, power factor, and line impedance affect the total voltage drop, especially at the far end of the distributor. So understanding such cases is essential for accurate voltage regulation and proper design of distribution systems. All right. In this slide, I want to begin solving the given example by calculating the impedance of each section of the distributor and expressing the load currents in complex form. So let me add a new student. The total impedance per kilometer is given as a combination of resistance and reactance, which is then uh, scaled based on the actual length of the sections, AC and CB. Using this, we can determine the impedance of each section individually. Next, by taking the voltage at the far end, point B, as a reference, the load currents are expressed in phasor form using these respective power factors. So the current at point B is calculated first, followed by the current at point C. Then, applying Kirchhoff current law, we determine the current following in each section of the distributor. So the section closer to the source carries the sum of both load currents, while the section near the end carries only the current of far load. So this is a KCL. So for for each point. This step is essential for accurately evaluating voltage drops in the next stage of the solution. So this is very easy. We have 200 meters from the resource divided by 1000 is converting to ohm. So impedance for distributor, impedance of section AC, CB, so can be calculated by this, and then we can calculate the current. So I2 is equal to I2 times cos phi2 minus J sine Q2, phi2. So, and current in section CB is equal to I2, IC here is equal to summation of this current and this current. And we can, this is very simple calculation. So, and then in this slide, I want to complete the solution by calculating the voltage drop across each section of the distributor using complex impedance and current values because they are complex form. So we have both impedance and reactance in our form. So first, the voltage drop in section CB is determined by multiplying the current in that section with its impedance, resulting in a complex voltage drop. Similarly, the voltage drop in section AC also can be calculated by using the corresponding current and impedance. These individual voltage drops are then added vectorially to obtain the total voltage drop across the entire distributor. So finally, the magnitude of the total voltage drop can be calculated by using the square root of the summation of the squares of the real and imaginary component. So we can use this one, this equation, and resulting in a value of approximately 17.85 volt. So this final result represents the actual voltage reduction from the feeding point to the far end of the distributor at point B here. Okay. In this slide, I want to introduce the concept of distributor feed at both ends. In this configuration, the distributor is connected to the supply mains from both sides, allowing power to follow from each end toward the loads distributed along the line. So unlike the single end feeding system, the voltage profile in this case is more balanced, and the minimum voltage does not necessarily occur at the far end. So instead, it appears at a certain point along the distributor, depending on the how the loads are distributed. Sorry, let me add a new student. And this minimum voltage point is not fixed and can shift as the load conditions change in different sections. So this type of feeding improve voltage regulation and reliability, and making it a more efficient and flexible option for power distribution systems. In this slide, I want to further examine the characteristics and the advantage of distributor feed at both ends. In each system, there is always a point of minimum voltage somewhere along the distributor, known as the point of lowest potential, and its location depends on the load distribution. A key advantage of this configuration is its high reliability. If a fault occurs at one of the feeding points, the distributor can still be supplied from the other end, ensuring continuity of service. Similarly, if a fault happens along any section of the distributor, the unaffected portions can continue receiving power from the opposite feeding points. So this ability to maintain supply under fault conditions makes double end feeding a preferred choice in modern power distribution systems. So that's why this is a main reason to use this kind of configurations. All right. This slide present an example of two-wire DC distributor AB that is feed from both ends, from here and here. We have two ends in this single line diagram with a voltage maintained at 230 volt at point A and 235 volt at point B. So the total length of the distributor is 200 meter from here to here, and several loads are tapped at different distance along the lines. You can see different loads here, 25 amp at 50 meter, 50 amp at 75 meters from point A, 30 amp at 100 meter, and 40 amp at 150 meter from point A. So the resistance of each conductor is given as 0.3 ohm per kilometer. This single line diagram is showing how current is distributed along different sections of the line, starting with an unknown current IA at point A and decreasing as loads are tapped off at various points. So points C, D, E, F. We have a different loads here. And the problem requires calculating the current in each section of the distributor and determining the minimum voltage along the line, as well as the exact point where this minimum voltage occurs. So let's how we can solve it. So this slide focus on calculating the resistance of each section of the two-wire DC distributor and determining the current supply from point A. So first of all, resistance of section AC, RAC. So resistance of 1000 meter length of distributed both wire, 2 times of 0.3 is equal to 0.6 ohm. And resistance of section AC, RAC is equal to 0.6 times 50 meter divided by 1000 meter is equal to 0.03 ohm. And for CD and DE, EF and FT also we can find depending on the length of the feeders. All right, first the total resistance of both conductors over 100,000 meter is calculated as 0.6 ohm based on the given resistance per kilometer. Using this value, the resistance of individual section AC, CD, DE, EF, and FB are also found proportionally according to their length. Next, the voltage equations equivalent between the potential A points A and B can be established by considering the total voltage drop along the distributor. The voltage at B is equal to expressed in terms of voltage at A minus the sum of voltage drop across the um, across each section, which where each drop is the product of current and resistance. So we can use this one. This is a KVL, right? KVL here. Voltage drop, voltage impedance point A is equal to um, voltage drop, potential voltage in, at point B minus the voltage drop in all of points. Okay, okay. All right. By uh, substituting the non-values and simplifying the equations, the current at point A can be calculated to be 33.34 amp. Using this result, the current in the first section of the distributor can be determined. So is equal to 8.34 amp, and showing how the current reduces after each load is tapped and uh, yeah, all of the customers are consuming the amount of the current. So this slide continue the analyzing by determining the direction and magnitude of currents in the remaining section of the distributor. After calculating the current at point A, the current in sections DE, EF, and FB are can be obtained by subtracting the cumulative loads, and the negative values indicate that the actual direction of current flows is opposite to the initial assumed direction. So I think I assume that everybody knows about this concept, right? This is a simple power flow. So this negative is because at the beginning we assume one direction for current, but after calculation we can find that what is the um, right direction of the current, right? So the as a result, the corrected current directions are shown with current following from E to D, not uh, from D to E because it is negative, and F to E and B to F, respectively. So this single line diagram clearly showing that the final distribution of currents um, along the entire distributor, and showing the current follow. This is a current follows, and toward point D from both ends A and B. This indicates that point D is the location where the potential is minimum here, and as a current coverage at this point, and finally the voltage at point D can be calculated by subtracting the voltage drop along sections AC and CD. So from the voltage from A, So if we want to find the potential at point B, so we know about the potential at point A, so we have some voltage drop here, we have some voltage drop here, so we can find the voltage drop here. And using the computed currents and resistances, the minimum voltage at point D is found to be approximately 228.875 volts. So this is a minimum voltage drop. This slide also presents a practical example of a two-wire DC distribution system with a total length of 600 meters, where loads are connected at different points along the distributor. The system is fed from both ends with the voltage at point A maintained at 440 volt, and at point B at 430 volt, and various loads are tapped at a specified distance, resulting in a gradual change in current along the line. So to analyze the system, we assume a current supply from point A and determine how it decreases as loads are drawn at intermediate points. By considering the resistance of the conductors and applying basic circuit analysis principles, we can calculate the current distribution in each section of the feeder as well as the total power losses in the system. So this example helps showing that how load distribution and line this resistance affect voltage levels, current flow, and overall system efficiency in DC distribution network. So this is similar to the previous one. So similarly, we have to find the total resistance and resistance of each sections, and then we can find the voltage drop at different points. So similar to the previous um, example, by applying Kirchhoff voltage law, the voltage at point B can be expressed in terms of the voltage at point A minus the cumulative voltage drop across each section. So the current in each section varies due to the tap loads, which is reflected in the equation by progressively decreasing current terms. So if we have a higher customers, so we will have more voltage drop. And also, if the distance of the customers place farther than the end at the beginning of the point, so it means that the voltage drop will be more higher. This formulation allows us to solve for the unknown current supply from point A and further analyze the performance and the efficiency of the distribution systems. So again, here in this slide, we present the final result of the distribution system analysis by solving the voltage equation. The current supply from end A is calculated to be 437.5 amp. Based on this value, the current distribution along the different section of the distributor can be easily determined based on the similar to the previous example, and showing how the current decreases as loads are tapped along the line. So similarly, the current supply from end B is found to be 417.20 412.5 amp, indicating that the load is shared between both feeding points. So it is also observed that point E represents the location of minimum potential in the system. Furthermore, the total power losses in the distributor is calculated by summing the losses in each section using the um, Ohm law. Do you know about this, right? The I power 2 times resistance. So this is a Ohm law formula. The final result shows that the total power losses approximately is around 14.705 kilowatts. So this example clearly demonstrates how current distribution and conductor resistance impact voltage levels and power losses in a DC distribution systems. So let's come back to the other configuration of the distribution networks, a ring distributor. So a ring distributor is a type of distribution system in which the network forms a closed loop or ring. In this configuration, the distributor is effectively equivalent to a stride distributor that is fed at both ends with equal voltages with two ends connected together to form a continuous path. So this arrangement improves the reliability and flexibility of the system as power can flow in more than one direction. Additionally, a ring distributor can be supplied from one or multiple feeding points, as I told you before, and allowing better load sharing and voltage regulations. Due to these advantages, Ring distribution systems are commonly used in urban areas where continuity of supply is highly important, and the high power supply security is very important for us. This slide presents an interesting example which demonstrates the calculation of currents and voltage in three-phase ring main distribution system. The system consists of a closed loop ABCD. ABCD, this is a closed loop fit from point A at 11 kV, supplying balance load at different points along the ring. Specifically, the loads are 50 amp at zero point 0.8 power factor lagging at point B here, and uh, 120 amp at unity power factor. Power factor is equal to 1 at point C, and 70 amp at 0.866 lagging power factor at point D. All load currents are referenced to the supply voltage at point A. So the impedances of each section of the ring are also provided with complex values representing both resistance and reactance for section AB, BC, and CD and DA. Using these values, the objective is to calculate the current following through each section of the ring, as well as the voltages at the bus bars of section B, C, and D. So this type of problem is important because it applies circuit analysis techniques, particularly the use of complex numbers and phasors to real power distribution systems. By solving this example, you can determine how current is distributed in a ring network, evaluate voltage drops across each section, and ensure that the system operates within accessible voltage limit while maintaining balanced load conditions are guaranteed. So you can compare this example with the previous example, radial systems. Okay, in this slide, I began the analysis of a ring main distributor using KCL, so Kirchhoff current law. The solution starts by assuming the current in one section, especially section AB. Um, as a complex quantity expressed in terms of unknown variables, using this assumption, the currents in the remaining sections B, C, C, D, and DA are determined step by step by subtracting the respective load currents at each node in their phasor form. So these load currents are expressed using their magnitudes and power factors, allowing them to be represented as complex numbers. After determining the current expressions in all sections, the next step involves calculating the voltage drop across each section by multiplying the corresponding current with the section impedance. This process transforms the problem into a set of complex algebraic expressions which will later be used to apply KCL and solve for unknown current. So we will go further step by step all of this. So this systematic approach is can be used and is essential for analyzing ring distribution systems accurately. So we have this is unknown uh, variables, and then we can calculate the current in section B, C, C, D, D, A, and the voltage drop in A, B, and B, C. So in this slide, we can complete the analysis of the ring main distributor by applying KVL around the closed loop A, B, C, D, A. So we have a KVL here. We can um, calculate the voltage drop here, and the voltage drop across all section A, B, B, C, C, D, and DA are first expressed in complex form using the previously derived current expression and impedances. Then these voltage drops are then uh, uh, added, and according to the KVL, their total must be equal to zero. This result in a single complex equation which is separated into its real and imaginary components. Since both parts must independently equal zero, we can obtain two simultaneous equations in terms of the unknown variables. So by solving these equations, you can see here these two equations, the values of currents can be determined and given the current in section A, B, and as a complex phasor. So this step is crucial as it finalizes the current distribution in the entire ring networks. All right. In this slide, we finalize the analysis by calculating the currents in all sections of the ring distributor and determining the voltages at different nodes. Using the previous obtained values of the unknown variables, the current in sections B, C, C, D, and DA are computed in complex form. Then, starting from the known supply voltage at point A, the voltages at points B, C, and D can be calculated sequentially by subtracting the voltage drop across each section. So similar to the previous question, just we have a little bit more complicated calculation. So each voltage is expressed as a phasor showing both magnitude and phase component. This step-by-step approach allow you to understand how voltage varies throughout the ring network and ensures that all node voltages remain within acceptable limits. So, this final stage is essential for evaluating system performance and verifying proper voltage regulations across the entire distributed in the ring configuration. So you can see voltage at supply end A. This is a um, we can calculate easily by this. For this is for three phases, so for each phases we can find voltages, and then voltage station B, C, and D can be find by using of KVL. Okay, this slide also presents a practical example of DC ring main distribution system analysis. It focuses on a closed loop network where power is supplied from a single point and distributed through multiple sections with given resistances. So the examples require calculating the voltage at different load points along the ring, considering the current drawn at each node, and it also extends the analysis by introducing an interconnector between two points A and C, which changes the current distribution and improves voltage levels. Overall, the slide demonstrates how network configuration and additional connections can significantly affect voltage regulation and performance in ring main systems. Okay, this slide introduced the analysis of a ring distributed operating V dot and interconnector. The diagram shows a closed loop distribution system with points A, B, C, and D, where power is supplied at point A with a voltage of 250 volts and different load currents are drawn at various points in the networks: 150 amp at B, um, 300 amp at C, and 250 at D. Initially, as unknown current I is this one, this is an unknown current, is assumed to follow in section A and B. This is just initial, this is assumption. So finally, we can check that this direction is correct or not. And based on this assumption, the currents in the rest sections are expressed in terms of I. So here, this is KCL, I minus 150. I minus 150 plus 300, 450. So do you know about KCL, right? So here I minus 700 in different section of the ring. So in the second part of the figure, the actual numerical values of currents are shown after solving the system. So this result indicate the true distribution of current in each section of the ring, such as 336.700 amp in AB, and so on. So we assume the right directions after solving this example. So this diagram clearly demonstrates how current is split and flows through multiple paths in a ring distributor, ensuring that loads are supplied from more than one direction, even without an interconnectors. So this is the result of this example. So this slide applied KVL to the ring distributor showing previously in order to determine the unknown current A. According to KVL, the the equations is equal to sum of voltage drop around the closed loop A, B, C, D, A must be zero. So this is a KVL. So therefore, the voltage drops across all sections A, B, B, C, C, D, and DA can be expressed in terms of I and their uh, respective resistance, forming a single equations. By substituting the resistance values and the load dependent current expressions into the equation, it is simplified and solved to obtain the current I is equal to 336.75 amp. Using this result, the actual current distribution in each section is confirmed and matching the values shown in the previous slides. And the slide then proceed to calculate the voltage drop across the each section by multiplying the current in that section by its resistance. So this is a voltage drop. It can be uh, simply calculated by using of this Ohm law. So these voltage drop are used to determine the node voltages at different points in the ring, starting from 250 volt at point A. The voltage at point B is found by subtracting the drop in AB, followed by further drops to calculate the voltage at point C. Finally, the voltage at point D is obtained, showing how voltage varies around the ring. So this analysis highlights how KVL helps in evaluating both current distribution and voltage profile in a ring distributor systems. So this slide introduced the analysis of a ring distributor with an interconnector and demonstrate how Thevenin theorem can be used to determine the current following through the interconnector. So this system is modified by adding a direct connection between points A and C, which changes the current distribution in the network. So first, The open circuit voltage between points A and C should be calculated as uh, E0. This is open voltage between A and C. So 200 minus 239.904 is equal to this one. Based on the difference between their previously determined voltages, then the the equivalent resistance R0 seen between points A and C is obtained by combining the resistance of the two possible paths between these 2 points. Um, so the resistance of the interconnector itself is also given as 0.02 points. So just this is a just KVL, KCL calculation on Ohm law. So it's very simple to calculate this value. And using these values, the network is simplified into a equivalent Thevenin circuit as shown in the right hand diagram you can see here. So this equivalent circuit consists of a voltage source E0 in series with resistance R0 and connected to the interconnected resistance RAC from here to here. Okay. And the current through the interconnector can then be easily calculated using this simplified model. So the left diagram is showing the updated current flows in the original ring, highlighting how the presence of the interconnector allows additional current to follow directly between A and C points, improving load sharing and voltage distributions. Okay. This slide also illustrates the analysis of a ring distributed using a Thevenin equivalent method to determine current distribution when an interconnector is present. And first, the Thevenin equivalent circuit is used to calculate the current following through the interconnector between points A and C by applying the relationship I is equal to E0 divided by R0, R0 plus RAC. This is a one KVL here. So the current can be found to be 252.4 amp from A to C. So following from A to C next, to determine how current distribute in the ring, we assume a current A1. This is uh, A to A to C. We assume A1. This is A1. So in section AB, and consequently, the current in section BC becomes A1 is equal to A1 minus 150 amps. So this is a KCL. So we know about this one, and this one minus 151 is equal to a IABC. And applying the KVL around the closed loop ABCD, so we can, the sum of voltage drop is said to be 0, and this leads to an equation involving the resistance and the current in each section, which simplifies uh, to we can find the voltage drop equal to 203.50 amp. So and using this value, the current in each section of the ring can be also determined as shown in the figure. So all of the current has been found. This is interconnected between A and C. So this current also can be calculated. This method demonstrates how Thevenin theorem simplifies complex network analysis and helps in understanding current flow in interconnected distribution systems. All right. This slide focuses on calculating the voltage drop across the different sections of the ring. distributor and determining the node voltages after introducing the interconnectors. Using the current obtained from the previous analysis, we compute the voltage drop in each point by applying Ohm law. V is equal to Ri. So this is Ohm law. So for section AB, the drop is equal to 4.063 volt, while for BC it is equal to 0.916 volt, and for AD so on. With this voltage drop known, we can now determine the potential at different nodes, starting from point A, which is at 250 volt. The potential at point B is found by subtracting the drop along AB, giving 200 245.93 volts. So similarly, the potential at node C and D can be calculated. The key takeaway here is that from this slide is that the presence of the interconnected Tor improves the voltage profiles across the network by reducing voltage drop in each point, leading to a more uniform and efficient distribution of electrical power. All right, I wanna start my lecture here in slide 54. So do you have any question? If not, I wanna